Hello everyone. So after a few questions on Worksheet 4, I thought I might make a movie about it, a little video here to kind of deepen the explanation that you might see on the key. This is a kind of an important worksheet because this one is your first exposure to a type of problem that I can pretty much guarantee will be on any typical AP Physics C Mechanics test, the lab-based problem. You're going to see these pretty much every unit and on every test we take and things. And you'll almost definitely see this on the actual test. So I'm going to go through these and give you some hints about what you're going to see and some things that hopefully you'll pick up sooner rather than later to help you do these problems. So this one is actually, as you can see from the AP test 2006. Usually that means it'll be a little bit easier than some of the ones you might see and won't have any calculus, although in this case, you actually could use some calc, as we'll see a little later on. So this is a lab where, if you read the statement here, right, you're trying to find the free fall acceleration g with this apparatus. The timer begins the recording when you release the sphere. It hits the plate at the bottom and stops the sphere. Should be a pretty accurate kind of thing to do. We don't actually have a set of equipment like this, but I've certainly seen them in the past. Now, right away, a couple of things to pick up in the initial statement is that they're giving you some symbols to use, right? G and D, and also here on the picture, right? So keep those in mind when you're writing things out, right? Sometimes they might actually do problems that are completely symbolic. Not this one, but sometimes. Then they give you some data. So ignore my writing in here for now. They give you the distance of fall in meters and the time of fall in seconds. They chose to put that on the left side, right? The column headings, we tend to put them across the top, so be it, right? They might give you different kinds of table organizations here. Then they ask you to plot distance versus time, including scaling the axes. Now, in this case, they've been nice. They've labeled the axes, right, and units. But sometimes they might just give you the blank graph, right? And you have to label the axes. Please remember, it goes dependent versus independent. And if you're not sure what the independent is, right, then you should always just follow the pattern here. It says distance versus time, right? So we always graph it distance and time. Because actually in this lab, right, you would be controlling the distance that you set it and measuring the resulting time. But as we did several times last year, we want the time on the horizontal axis to make the slope mean particular things, right? But again, the clue is in this. Now, could you graph it backwards? Yeah, they wouldn't take points off. Just means that some stuff later on is going to be a little more difficult. So in this case, they ask you to graph. Notice my scale, right, makes the data big. I didn't smush the data over here in the corner, right? I didn't choose the same scale for the two axes, because I don't have to, but I did make it a consistent scale. 0.1, 0.2, 0.3. It's not like 0.1, 0.2, 0.5, 0.7, something like that. Right? Consistent scale up the side. I graph the points. It says to sketch the smooth curve that best represents the student's data, which I hope you look at and go, hey, that looks like a parabola, top opening parabola. So the next step is, you've got this distance and time data. Now I want to make a graph that creates a linear relationship between the two quantities. Well, you've done enough graphs and linearization last year that hopefully you remember that when you see a top opening parabola, what do you do to the horizontal variable? You square it. And so that's what I suggested here. Now notice it says quantities. So if you just write time squared, that's a quantity. Right? You need to put both of them in there. I've seen people lose a simple point. They knew exactly what they were doing, but they didn't answer the question. Right? So you need to say distance and time squared. Now, could you do square root of distance and time? Sure. I don't know why you would. It makes life more difficult, but you certainly could. They would allow you to do so as long as your work later, works. Asks you to calculate values. Note, label the row heading including units. Again, simple mistake that's sometimes made is that people don't put the row heading and the units in here. So I'm doing times squared in seconds squared, and then I actually square the times and write them in there using a reasonable number of sig figs. You could probably keep this down to 2 sig figs if you wanted. They'd be okay with that because there were 2 here. The AP doesn't really use sig figs. They just want you to keep it in the ballpark, right? So they might not want you to write like 8 digits or something if that's what your calculator says, but you know, try to keep it reasonable. So then we make a graph of that. Notice in this case we have to label the axes. Don't lose the point for the graph because you neglected to label the axes. So distance in meters times squared in seconds squared. Now note here, I chose a scale like this, which does compress the data somewhat, but it's convenient scale. Right? Notice there's not enough lines out here for me to do this. Like I can't go 0.1, 0.2, 0.3, 0.4 would be all the way over here, and I need 0.4. Right? So, you know, again, you have to choose a scale that's convenient for you. Don't choose something weird like every one of these big lines is 0.13, because how are you going to figure out what these are in between, right? Pick a nice scale, but try to make the data as big as possible. Okay, they'd be all right with that. And plot your points, right? Make big points. And then it says, often this is a separate question, but in this case it says sketch the line of best fit, right, to the points. Notice how I have points. Notice how I draw a single straight line, right? And notice how some of my points are touching, some of my points are a little off. Right? That's just going to depend on the data they give you. Make sure you have lines or points, above and points below. Try to average everything out. Draw one straight line, have it go all the way back through the axes. You'll notice that I made a choice here to make my y-intercept 0, 0, which I hope makes sense given the apparatus. Right? That at 0 time, at 0 distance, it would take 0 time to hit the pad. Hope that makes sense. So I've drawn the line of best fit through there. Now, we get to part F. Here is something I hope you will remember for every single one of these problems, these lab-based problems. This is almost always true, all right? And it's kind of an unwritten rule when doing these lab-based problems in AP Physics C. Once they ask you to draw a line of best fit, the very next question almost always has something to do with the slope of that line of best fit. Notice I did not say the slope of your data points, but the slope of your line of best fit. Sometimes the answer to the question is the slope of line of best fit. Oftentimes, though, it's just related to the slope of your line of best fit. But it's almost always got something to do with that. Now, in this case, they were explicit. They said using the slope of your graph in part E, all right, calculate the free fall acceleration in this experiment. But they may have just said using the graph in part E, calculate the acceleration, and not said using the slope. That's probably more common. Remember, this is a Physics B question, an old school Physics B before AP 1. Right, so this is, they helped a little more. Okay? On an APC question, they would rarely actually tell you to use the slope. They just say, figure out what the acceleration is by using your graph. But that almost always means finding a slope. And if you're going to find a slope, you need to show them how you found a slope. Remember, slopes take 2 points, rise over run, change in y over change in x, if you will. You need to pick those 2 points carefully. Do not use data points. Okay? They almost always save a point in the rubric for using points on your line of best fit. The whole point of a line of best fit is that it's the best approximation of your data that you can get. Right? So even though you're eyeballing it, it's better to use that than data points. So you would pick 2 points. Okay? You might notice here I picked 0.3 and I figured about 1.5. I picked this point because I figured it's pretty much through the crosshairs. And I picked 0.2 and 1, right, which again goes right through here. You could pick 0, 0 if you want. If you do, make sure when you're calculating your slope and showing your work, you put in 0, 0. All right, because you need to show them that you use 2 points, not 1 point. recognize here, if this had a significant y-intercept, 1 point's not going to get you the slope, right? 2 points will always get you the slope. So you should show your work. And notice how I also calculated units for the slope. Okay? Again, I've seen lots of people give away silly points on tests here because they do the slope, but they don't show their work. So I can't tell if you've used points from your line of best fit. They neglect to put units on their slope, right? And often that's one of the points in the rubric. Okay? So again, always, 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 the question after you draw your line of best fit almost always has something to do with the slope. So now in this case, we've got the slope. Right? It ends up being 5.0 meters per second squared. Now you might be looking at that and saying, oh, those are acceleration units, so this must be the acceleration. You would be wrong. 2 ways to figure that out, okay? Here's what they probably intended for you to do, given that this is from an old physics B test, AP B test, and therefore non-calculus based, okay? Although I'll show you the other method in a moment here. They probably want you to go, well, this is free fall. And free fall is uniformly accelerated motion, and therefore the kinematic equations apply, like our ever-popular third kinematic equation. If I replace the variables here with the ones given in the problem, our displacement becomes d, right? Technically it's negative d, but g is also negative, right? Our initial vertical velocity is 0, so this whole term drops out. So this is what we have left. Compare this to the graph. You made a graph of distance versus time squared. Well, look at the equation. This is an equation of distance and time squared. So if we use y equals mx plus b setup of the graph, y equals mx plus a y-intercept of 0, I hope you can see here that your slope is actually 1/2 g. Do you see that? Right? Third kinematic equation. You might remember we actually did this, in a lab in honors. Right? That means that g is actually twice your slope, which is the much more Earth-like 10 roughly meters per second squared. And notice here, they'll take anything in the range of 9 to 11 here. So they give you a little, a 10% bump on either side. Same thing over here with the slope, right? So they take anywhere from about 4.5 to 5.5. So they give you a range of values because you're eyeballing this. Now, by the way, if you know how to use your calculator well enough, you could have put in your data, your distance times squared data, right? And you could have done a linear regression on your TI calculator or your other calculator if you know how to do it. You are fully okay to do that, as opposed to hand drawing a line of best fit, which you still need to draw, but using it to find your slope. But if you do that, you need to tell them. So like over here, I would write slope equals 5.0 meters per second squared found by doing a linear regression on my calculator. Okay, they'll be perfectly fine with that, but they would want to know it. Otherwise, they're looking for work. Okay, so if you do something fancy with your calculator, good on you, but you got to tell them. Okay, so notice it's got units on it, right? The answer's got units on it, and you got a range of values here. So think about that. Now, because you are APC students, there is an alternate way of doing this answer, okay, which I kind of like actually from a calc standpoint. Sorry, it's right down here. Make a math model of your linearized graph. X equals the slope, t squared, plus 0, right? Well, now you've got the position as a function of time. Well, as we know, we can find the velocity function with respect to time by taking the derivative of the position with respect to time. Multiply by the exponent, subtract 1 from the exponent. You get 10 meters per second squared, t. Take another derivative, second derivative of the position with respect to time, and you get the acceleration. Multiply by the exponent, which is a 1. Subtract 1 from the exponent, t to the 1 minus 1 is t to the 0, which is 1, and you get your acceleration. Now, on an APC test, they would allow either method. They don't care how you get there, but you need to show them your work, okay? You don't need to write out all the steps to the derivative, but man, I would highly suggest you show this and this so that they know how you got there, okay? If you just write 10 meters per second squared is my G. You just write the answer. You may not get full credit because you did not show any work and they don't know how you got it. Okay? You might get a point for the answer. It depends how they wrote the rubric. Right? They might write the rubric for, showing the calculus or relating it to uniformly accelerated motion. Right? It could even be a couple of points where they write something like showing that the that the free fall acceleration is twice the slope, or doing two derivatives or something like that, right? So make sure you're watching that. And then the last answer, I hope, is fairly obvious, I think. There's lots of different answers that would work, but given that they only did one trial, right? If you think about doing labs in class, we often did several trials and took an average to reduce personal and kind of random error. I'm not quite sure what else would work in this case because you've already got very high-tech equipment. So, it'd be hard to improve the accuracy of the equipment. It's not like we were using a stopwatch and a meter stick, right, to do this and just dropping a ball. If we were doing that, then there would be all sorts of things you could write about using fancier equipment like the actual apparatus or photo gates or motion detectors or really anything else that you know how to use and that we've used in a lab. Right? You can expect that the readers will know common lab equipment. And although ours is kind of on the high end of common, they're going to know about those things. Right? So as long as you kind of give them a decent name and an explanation of what they do, right, it'll work. Note that I'm writing in full sentences, right? And I'm explaining why this would improve the accuracy as well as stating one way. So you okay with this one? All right, you can take a look at it again. But again, one of the key things, once you draw your line of best fit, next answer usually has something to do with the slope of that line of best fit. So let me go to the next question. We actually did this lab last year. Right? It was a new for me way of showing uniformly accelerated motion. Right? We took the fan cart, attached it to a cart, and let it run across the floor. We actually put little blocks down every so many seconds and then measured, if you remember. So they did a similar kind of lab, and they have a graph of position versus time. A little more conventional to the way we wrote it with the column headings above and the units. Note they used meters and seconds here. Now here's a little more APC way-ish of doing it. So note they're not going to ask you this time to actually make a graph, right, of the original data, and then by looking at that graph, decide what to do to linearize it. They're just going to ask you, how do you linearize this data? Right? What variables should you use? So they are going to expect that you know that this will be a uniformly accelerated motion, given the constant force of the fan, and that in uniformly accelerated motion, position is proportional to time squared. Or you could do this, but that's harder, right? So they're going to kind of make an assumption here that you know what you're doing. Yes, if you have time, you could quick sketch out a graph here, but hopefully you don't need to. Right? You recognize the kind of motion that's going to come, and you know how to linearize it. Note again, it says quantities, so I need to list both. Right? If I don't list both, I won't get the full point. Then it asks you to calculate the values for those variables, put them in the data table, and label the row heading including units. Silly point to give away if you don't label and units. And note, this is something they often do. They give you a row over here in case you decided to mess with the position, and a row over here in case you mess with the time. Oh, did they do that on the first question? Notice how they did that in the first question too, right? A row above and a row below. So they're trying not to lead you in this lab. They're going to let you do the harder one if you want to. It just makes life harder in the end. And again, I'm using a kind of consistent, looks like they're using about 3 sig figs in here, so I'm keeping 3 in here, right? Just don't get crazy with the sig figs. Don't over round. Don't throw in 8 or 9 or something like that. Now we get to the fun part. Come on, you. Here we go. Graph. So notice here, I have labeled the axes with units. Silly point to give away. I've put position on the vertical and time on the horizontal, time squared on the horizontal, because that's what makes the most sense if we're going to do the rest of the problem later. It's also the way we've done pretty much every lab in here, which is to put time on the horizontal axis. They didn't really give you the same prompt as they did in the previous problem. Note they didn't say like graph these variables or this versus this, but I think it's still, how you would do this lab. Again, in this case, notice though, look at the numbers, right, in our data table. These are all perfect, which would lead me to believe that here you go. The student measured the position of the fan cart at various times. So that means time was our independent variable, position was our dependent variable, and therefore we should make a graph with position on the vertical axis and time squared on the horizontal. You graph your points. This might be like 2 or 3 points on this. Okay, and this is before the line of best fit that I drew in later. You'd get a point for like labeling your axes well. You'll get a point for graphing your points well. You'll get a point for using a scale that makes the data fairly big. And note here again, I chose a nice scale. Yeah, it didn't fit like perfectly, but it's going to make it easier for me to graph my points, all right? I didn't smush it in the corner. I didn't go like 1, 2, 3, 4, right, and have my last point here and make this one, 5 and 10 so that my whole graph took place right here. Right? I tried to spread it out, but I chose nice things. Right? Don't use fractions and heavy-duty decimals and all that. Make nice choices. Next part, sketch the line of best fit. Again, you're eyeballing it. By the way, you can bring a straight edge. You can bring a ruler into an AP test. And I would suggest that you do. Right? Because you're probably going to have to draw at least one line of best fit on the free response. So you can use it to draw a nice straight line. Don't connect the dots. Don't have a line that moves all over the place, otherwise you're going to lose a point. It needs to be straight. I chose to follow it back towards 0, 0 again because in this lab, that certainly makes sense, makes logical sense in the data. It's not a point, right? They didn't give you that point in the data, but it makes logical sense that I put it there. And then notice how my points kind of fall to either side, right? You see I've got several above and several below. The rubric might say something like 1 point for at least 2 points above your line and 2 points below your line. Right? So as long as it's there, it might change slightly by slope. They're going to give you a range of values. Okay? But there you go. And now the magic happens. Look at part E. Using information from the graph, create an equation that describes the position of the fan cart as a function of time. Now note here, it said nothing about the slope of your line of best fit, but you can't create a math model without the slope. So as I said before, the question after the line of best fit is almost always about the slope. And how do you find a slope? You pick 2 points. Notice how I decided to use 0, 0, but I showed using 0, 0. So that they knew I chose that. And I chose, let's see here, 5, 2. Oh yeah, because see that pretty much went pretty close to being right straight through. There wasn't really other good points. I mean, otherwise I got to estimate, right? So I'm trying to find good points to use. Do not use data points. I am showing my work. Again, if you're doing a linear regression on your calculator, tell them you're doing a linear regression on your calculator. Put units on your slope. So y equals mx plus b because it's a linear graph. Y is the position. In this case, I don't think, they didn't give a variable. So they didn't give you a d like they did in the first one. So I'm going to use the conventional variable for position, which is x. That equals my slope, t squared. And then part F, they want the acceleration of the fan cart. Well, 2 methods again. I'm guessing in APC, they actually want method 2 because they had you make the position versus time squared, right, function. So once you have this function to find the acceleration, you take 2 derivatives. Note, I did not show a ton of work here, but I did show them what I was doing. Right? And again, you want to do that, okay? You don't have to always show a ton of work. Like, you don't have to show multiple steps of algebra in a problem, but you ought to show where you started from and where you ended, okay? Because sometimes there are points in the rubric saved for that. This might be a 3-point problem, okay? And one of the points might be, if you're using this method, okay, took the derivative of the position with respect to time to find the velocity function. Second point, took the derivative of the velocity function with respect to time to find the acceleration. Third point, for a correct answer, consistent with what they wrote in part E. So whatever your slope was here, as long as you were consistent. And by the way, even if you completely messed up your slope up here, right? So, I don't know, you picked points that you weren't accurate with your points, you flipped it upside down accidentally, right? You did x over y instead of y over x, right? They would probably give you full credit on this question as long as you did the right physics. Okay? So that point for an answer, they're probably going to let you go with, as long as it doesn't make the answer like super bizarre. Right? If you're accelerating, because you flipped this over, you had a huge number here that just makes, oh, my acceleration is 200 meters per second squared. I mean, a little fan cart, unless that's like a jet engine fan cart, is not going to accelerate that quickly. Right? So your answers need to be reasonable. But in this case, the inverse of 0.8, 1 over 0.8 is, 1.5? Something like that? No, that can't be right. 1.25? But anyway, it's a number that's not unreasonable, right, for a fan cart. The other way to do this problem, like the last one, is to realize that this is uniform accelerated motion, which of course you should know because position was proportional to time squared, which is a hallmark of uniformly accelerated motion, and the kinematic equations. So you could relate this equation to the appropriate kinematic equation, right, which is the ever popular third. Initial velocity is 0, starting from position 0. You get this equation, compare it. Notice you've got the same y variables, the same x variables, the same 0 y-intercept. That means the slope is 1/2 the acceleration, or the acceleration is 2 times the slope. And you get the same answer. Again, even though I believe they probably would have wanted calculus on this problem, given the way they set it up, they wouldn't care if you don't use calculus, if you recognize this, right? Then they would be like, fine, they understand what it is, and you would get full credit either way. The rubric would be written differently, but they're good with that, right? They usually try to give credit for as many different variations as possible. And if you have something truly unique, they're going to stop and look it over and see if it works, right? As long as you've shown enough work for them to be able to follow what you're doing. Right? And your stuff's written out nicely, which is why I keep telling you, look at my keys, look at how I write stuff out, and start to step up your game as far as writing stuff out on your worksheets and test works, now that this is APC, right, and not just regular old honors physics. So I hope this helped you understand this worksheet a little better and prepared you a little more for the type of question you're going to see on plenty of AP tests, like probably nudge nudge, our first test that we get to with the lab-based problems.